this video, we are going to work on problem 3.5.2 from the textbook. Prove that each of the following functions is not uniformly continuous on the given domain. The first function is the squaring function on R. The second function is given by f of x is equal to sine of 1 over x on the interval 0, 1. And the third function is the ln function on the interval from 0 to infinity. Before solving the problem, let me recall the definition of uniform continuity. Let D be a non-empty subset of the real line. A function f defined on D is said to be uniformly continuous on D if for any epsilon greater than 0, that is delta greater than 0, such that whenever u and v are in D and the absolute value of u minus v is less than delta, then the absolute value of f of u minus f of v is less than epsilon. Based on the definition of uniform continuity, we can prove the following property that is called the sequential criterion for uniform continuity. The function f defined above is uniformly continuous on D if and only if, whenever we take any two sequences un and vn in D such that the limit of un minus vn as n approaches infinity is 0, it follows that the limit of f of un minus f of vn as n approaches infinity is also 0. This property is very important, especially when we want to show that a certain function is not uniformly continuous on a given domain. So if you can show that there exist two sequences un and vn in D such that the limit of un minus vn as n approaches infinity is 0, but this limit is not 0, then we can conclude that f is not uniformly continuous on D. Now we are ready to work on the first problem. Our strategy is to use the sequential criterion for continuity by showing that there exist two sequences un and vn in D such that the limit of un minus vn as n approaches infinity is 0, but f of un minus f of vn does not converge to 0. Okay? And this is the graph of the squaring function. Based on the behavior of the graph of the function, we can see that if u and v are not, even though u and v are close to each other, f of u and f of v may be far away from each other. That suggests us to use the following sequences in order to prove that f is not uniformly continuous. Un is n plus 1 over n, and vn is n. Okay? As you can see here, un minus vn is 1 over n. It converges to 0 as n approaches infinity. And we are going to show that f of un minus f of vn does not converge to 0. Now, we define the following sequences. Un is equal to n plus 1 over n, and vn is equal to n, and n here is in the set of all natural number. Okay, then we see the following: the limit of un minus vn as n approaches infinity is the limit of, as you can see, un is n plus 1 over n, and then we subtract n as n approaches infinity. This is the limit of 1 over n as n approaches infinity, and it is 0. Okay? We also see that f of un minus f of vn is equal to n plus 1 over n squared minus n squared. Okay, so this is equal to n squared plus 2n times 1 over n, which is 2. Okay? And here is 1 over n squared. And then we subtract n squared. Okay? So this is equal to 2 plus 1 over n squared, because we can simplify n squared, and as you can see, it converges to 2 as n approaches infinity. Okay, so we have found two sequences un and vn in the domain of the function, such that the limit of un minus vn as n approaches infinity is 0, but f of un minus f of vn does not converge to 0. Therefore, f is not uniformly continuous on R. Now, let us focus on the second problem. We are going to show that the function given by f of x is equal to sine of 1 over x is not uniformly continuous on the interval 0, 1. It is a good idea to look at the graph of the function. And we realize that the graph changes a lot when x is near 0. Okay, and you can also see that if x is 0, 2 pi, 4 pi, 6 pi, and so sine of x is equal to 0 in general. Sine of 2n pi is equal to 0 for all n in n. And also sine of pi over 2 plus 2n pi is equal to 1 for all n in n. Now suggest us to use the following sequences to prove that f is not uniformly continuous on the interval 0, 1. un is 1 over 2n pi, and vn is 1 over pi over 2 plus 2n pi. We define the following sequences. In the interval 0, 1. un is equal to 1 over 2n pi, and vn is equal to 1 over pi over 2 plus 2n pi. Okay, you can easily verify that both un and vn are in the interval 0, 1 for all n in n. Okay, then the limit of un minus vn as n approaches infinity is the limit of 1 over 2n pi minus 1 over pi over 2 plus 2n pi as n approaches infinity, and you can easily see that this limit is 0 by the difference rule. The first limit is 0, and the second limit is also 0. Okay? And at the same time, f of un minus f of vn is equal to sine of you take 1 and you divide it by un, so it's 2n pi minus sine of pi over 2 plus 2n pi. Because over here, it is sine of 1 over pi over 2 plus 2n pi. Okay, so that's why we get this. And as you can see, this is 0 and this is 1. So this is minus 1, and it converges to minus 1 as n approaches infinity. So we have found two sequences un and vn in the interval 0, 1 such that the limit of un minus vn as n approaches infinity is 0, but f of un minus f of vn does not converge to 0. Therefore, f is not uniformly continuous on the interval 0, 1. Similarly, we can show that the L-length function is not uniformly continuous on 0 to infinity. And by looking at the graph of the function, we can see that when u and v are near 0, u and v are close to each other, but f of u and f of v could be far away from each other. So you can try with the following sequences. Un is 2 over n, and Vn is 1 over n. We can also show that Un minus Vn approaches 0 as n approaches infinity, but f of Un minus f of Vn does not approach to 0, and therefore f is not uniformly continuous on 0 to infinity.